Hello everyone, welcome to our webinar on vibration and noise analysis in COMSOL Multiphysics. My name is Arpad Forberger and I'm an application engineer at Gamax Laboratory Solutions Ltd. Today we are going to take a look at COMSOL and how to set up physics for calculating radiated sound for vibrating objects. I will walk us through some models to give you a chance to see the software up close and see how it might help you in your work. COMSOL is a multiphysics modeling, simulation, and application design environment where all of the steps of a simulation are integrated into one user interface, from the initial setup to the solvers to post-processing to putting together a custom built-in application. A COMSOL model allows you to couple together physical effects the way they are in the real world, which we refer to as multiphysics. Once you have completed your simulation, the software also allows you to create a customized app from the model, which enables you to deploy the analysis capabilities and results to collaborators, customers, or even colleagues around the world. This is our product suite. We have add-on products that can be combined with the COMSOL Multiphysics core package to enable simulation of specific physics phenomena across a range of application areas. These can all be combined with each other. We have modules for electrical, fluid, heat, mechanical, acoustics, and chemical simulations, as well as several multi-purpose modules and tools for interfacing with external software. COMSOL is very flexible. It contains many predefined physics interfaces, but also allows you to define your own custom physics and equations. And today's webinar is focusing on the features and capabilities of the acoustics module, rotor dynamics, multi-body dynamics module, and features from the structure mechanics module. Here you can see the branch of the acoustics module and what kind of physics you can couple and create simulations in COMSOL Multiphysics. Today we will look into the pressure acoustics, frequency domain physics node, and some boundary elements node. So this is a new feature in COMSOL Multiphysics. You can see how you can set up a boundary element problem and couple to a finite element problem. And we will also use the acoustic shell interaction frequency domain subnode to set up some model. Application areas where can be used this feature in COMSOL Multiphysics: for designing and optimizing hearing aid, for designing concert halls, any rotating machinery, gearbox that can generate noise, lots of noise in various effects, washing machines and household appliances, muffler design, and you can include also the porous domains to stiffen to dampen the vibrations of such devices, and also for loudspeaker design. That's another field where these physics nodes and couplings can be used in COMSOL Multiphysics. Today's model where we will start is a simple one. So we will couple different physics. So we will have a shell at the bottom of the cylinder. This is a vibrating shell, so we will use the shell physics interface here. Inside the cylinder we will use the acoustics physics node, so we will use the finite element formulation to calculate the sound pressure level and the acoustic pressure inside the cylinder. And we will also add the boundary element method acoustics physics interface, and we will couple it to the other two physics to set up another calculation, so we can visualize and calculate the sound pressure level and the acoustic pressure outside the physical domain anywhere without any limitation. So that's a new feature. So we can create hybrid models coupling the finite element acoustics to boundary element acoustics. So if we go into COMSOL Multiphysics, we can set up the model by selecting the model wizard. So we will go for a 3D domain, and from the acoustics acoustic structure interaction node we will look for the acoustic shell interaction frequency domain. So we can add this to our selection. you can see that the multiphysics coupling is automatically detected and created, and for the study we will use an eigenfrequency solver. For the geometry we will set up a cylinder. For this purpose we change the unit settings to millimeters, and we will use a very simple geometry for this purpose. So we set the radius to 38 millimeters and we set up the height to 255 millimeters. Okay, so that's the geometry we will use. So here at the bottom we will use the shell physics interface, and inside the domain we will apply the pressure acoustics frequency domain physics interface. Selecting the materials, so we need to assign some materials. So we will use a material from the built-in library. So we will use structural steel, but instead of domains we will assign only to boundaries, since we are using shells. So we will attach this material to this surface. Okay, and for the internal part we will add air. Okay, so we will have air in the cylinder. That's it. Okay. Geometry is done, materials are done, pressure acoustics frequency domain. That's the settings we have here, and from the shell physics interface we remove all the boundaries and we select only the bottom surface, since we are using this shell interface only here at this boundary. Okay, change the thickness to 0.38 millimeters. Okay, and if we want we can add some boundary condition. So we can set up and solve for the stationary solver or for eigenfrequency solver, or we can set up frequency domain solvers. In this case, if you have some radiation, some vibrating domains, you can add a body load or a rotating frame whatsoever, or you can add a prescribed velocity or acceleration. So if you have some velocity profile or acceleration profile, you can add this kind of excitation to any surfaces in the shell interface. So that's where we are, and here you can see the coupling between the two physics is automatically generated. So from the pressure acoustics frequency domain to the shell interface, the coupling is automatically done here. I have a saved solution, so I open up that one and we can see how it looks like. Okay. So for the boundary element method, it may take some time for solving such a problem. So I have this solved version here. So if we go back here, we have the same two physics, pressure acoustics frequency domain. We have a shell interface with the same thickness at the bottom surface. Okay, and what's new? We have this pressure acoustics boundary elements physics interface. As you can see, we have this very thin indication of a layer here. That means that we place some sound soft or sound hard boundary in front of our cylinder, and this can be found here in the symmetry infinite boundary condition subnode. So as you can see, I've set up an XY plane 0.5 meters away from the cylinder, and it says that it's a sound hard boundary, so we will have reflections there. All of the other planes are switched off, so surrounded by this cylinder we have free air, free domain. And here in the materials section you can see that there is a new air. Material, it says it's infinite void. As you can see on the right hand side in the geometry in the graphics node there is no selection. It means that this air material is assigned to the infinite void that surrounds our cylinder. So we have two acoustics interfaces, one finite element formulation that setups for the pressure inside the domain. We have a shell interface at the bottom, and we have a pressure acoustics boundary element. So that's a hybrid model that accounts for pressure changes and any far field sound pressure level calculations outside the cylinder, outside the drawn geometrical domain. And in the multiphysics node we have the previously seen acoustic structure boundary coupling between the two physics, and we have a new physics coupling between the pressure acoustics boundary elements and to the pressure acoustics frequency domain, which is a finite element formulation. And from the domain solver we have a frequency domain solver that solves for the three physics interfaces and for the two multiphysics coupling. So we have some plots here. In the follow-up email you will get all the models and presentation slides. So I want to stress some plots here. So we have some acoustic pressure plots, the isosurfaces inside the cylinder, so we can visualize these. Okay. For different eigenfrequencies. So this is the acoustic pressure field, and we can also plot the mode shape of the shell because we have a shell physics interface. So we can also plot the mode shape coupled to the pressure inside the cylinder, so we can change between the modes and we can see how it changes the pressure inside our computational domain. And since we have a boundary element method, we can visualize the pressure or sound pressure level outside the domain quite easily. As you can see, we have this grid study that stores the solution of the boundary element method, and we can visualize quite easily in this sense the sound pressure level outside the cylinder. As you can see, we don't have any coloring inside the cylinder since we use a finite element formulation inside, so we can visualize only now outside, but we can use in any distance, any number of planes we can place anywhere. You can put any coloring and any feature that you would like to use. So with the boundary element method you can quite easily calculate values, whether it's a sound pressure level or acoustic pressure outside in the free air. It's quite easy to do that since it's a boundary element method. So you don't need to create mesh outside the geometry. As you can see, we have only one mesh for the finite element formulation, and for the boundary element formulation there is only one plane that's a sound hard boundary. The next example I would like to show you, it's a bit more complicated. So we have a multi-body dynamics physics that accounts for the rotation of the gears and the pairs and the gear pairs, and it will cause vibrations on the outer shells, on the outer boundaries of the gearbox. And outside the gearbox we have a finite element formulation to account for the acoustic pressure and the noise generated by these radiations that come from the gearbox. So if we go back to COMSOL and we look for in the application libraries for this gearbox, we can open up, no, sorry, it's a gear train, it's another one. Okay, gear train. So instead of the shell physics interface, here we use the multi-body dynamics interface to take into account the motion of this gearbox with the gear pairs. So we have this component 2 which says multi-body dynamics. So we calculate the noise and the radiation, the vibrations through the multi-body dynamics and the pressure acoustics frequency domain solver. So we have this one physics interface. We have these gears defined one by one, and here we have the pairs defined one by one. So this is the physics interface for the multi-body dynamics. And because we need to map the vibrations from the multi-body dynamics to the acoustics field, we use an operator, a so-called general extrusion operator, that simply maps the vibrations from the multi-body dynamics physics interface to the pressure acoustics frequency domain physics interface. So we use two separate physics, two separate components, and we hide some of these surfaces we can look into the model. So this is a new geometry, that's for the pressure acoustics. And since we already calculated the vibrations from component 2, that's for the multi-body dynamics, we can simply add a normal acceleration and use the results of component 2, because that's where we calculated the vibrations. U, V and W, they are the vibrations in the X, Y and the Z directions. So that's how we map a solution from one physics interface to another one, and here we simply calculate the pressure outside the gearbox and we can visualize. So here we have a time-dependent solver for solving only the multi-body dynamics mode to calculate the vibrations, and then in study 3 we have two steps. So we have this time to frequency FFT, so we convert the time-dependent solution to a frequency FFT solution, and then we can use the result of this solver as an inlet to the frequency domain solver. So we are searching around F0, which is 200 Hz. That's the particular frequency that we would like to visualize. So now if we go to the results node, we can visualize the sound pressure level and the vibrations as well here inside the gearbox. So here we have two color scales, one for the acoustic pressure and outside the gearbox, and one for the rotations, the displacements, as you can see here. So this is how you can set up a more complicated model using more physics and more realistic 3D geometries with interactions between whether it's a shell interface or a multi-body dynamics interface, and to couple to a finite element or a boundary element acoustic formulation. You can find more applications and models at COMSOL.com and the application library, and all of these models can be found at COMSOL's website, and you can download also the documentation there. So to summarize and to wrap up my demo, what we have seen here, that you can set up multiple and several multiphysics couplings between different physics interfaces, whether it's a shell to a finite element acoustic formulation or a finite element acoustic and a boundary element acoustics formulation. And you can also create more sophisticated ones, so you can include whether a solid, a shell and a finite element acoustics formulation, whether it's a car interior cabin or a loudspeaker that you would like to calculate and visualize the pressure fields and the directivity plot. So you can use time to FFT solvers or an eigenfrequency solver or a frequency domain. That's some of the solvers that we have seen in today's webinar. There are much more that you can do and you can calculate in COMSOL Multiphysics. And if you are looking into more details about these models and more models, you can go to the COMSOL's special edition on the acoustics. You can see the link here, so you can freely download or read online this documentation and this newspaper. So if you are more into acoustics and you are more interested in several ways how you can interact with COMSOL, feel free to go to COMSOL.com and look into this special edition. So if you would like to try out the software, you can write us, connect to us directly for a free trial, so you can evaluate the software's capabilities, and you can look for other events and also look for the recorded webinars. This is also recorded, so if you found this a bit fast, you can go back later and you can see the published archived webinars to recatch, and you can find lots of models and user stories also at our website and at COMSOL.com. So I thank you for your attention, and if you have questions, feel free to write here in the chat window and write directly to our website or to our email addresses. So thank you for your attention and see you next time.
Thank you very much for your introduction. It was very good.
Nem, még nem nevem le. Egész sokan voltak. Okay. Teddy. Rémusz.
Te felső vagyok? Most te felső vagyok?
Hol nincs? Igen, mindig te vagy a legfelső, igen.
Akkor nézzünk.
Aha, igen.
De miért lépett úgy be, mint hogyha én lennék az előadó?
Nem értem, meg át
akkor
is
addig
húzta.
nem merek kilépni.
Ne. Meg át is húzta azt a gömböt oda, hogy te lettél az előadó, azt nem értem.
Nem tudom, pedig nem vagyok belépve.
Nem tudom, fura ez a Webex.
Nem.
Furán működik. Oké.
Kérdezhetek?
Ja, hogyne.
Nagyjából azért érdeklődök.
Jó.
De hogy ugye elmondod, hogy te hogy szoktad felépíteni a webinárjaidat?
Az elején, igen.
Erre próbálunk valami best practice-t kitalálni.
Az elején van ez a fix diasor, az ugyanaz.
Igen, de hogy ezekben x mi volt, hogy összefoglaltad, hogy miről szól a konzol.
Igen, hogy mi is az, miket lehet vele, hát ugye ez. Még vannak benne, jó. Tehát ugye ez, hogy mi az általánosan, akkor milyen modulok vannak, most melyiket fogjuk használni, igen. Akkor ugye, hogy konkrétan most melyeknek a funkcióit fogjuk használni.
Igen.
Aztán még lejjebb megyünk, ugye itt az általános, hogy most mit használunk, és akkor azon belül, hogy az akusztikán belül miket fogunk használni, tehát még lejjebb megyünk. Hogy tik, ez mi az egy-két dolog, amiről szól ez konkrétan.